In part A, they want us to draw the Lewis dot structure for nitrogen and NH3, and these two I'm hoping by now should be relatively easy because they show up quite a bit. But if not, remember, just tackle them with the strategy we always use, which is we connect them, we count how many valence electrons there are, and each nitrogen is going to contribute 5 electrons for a total of 10. And you remember we started around the outside. There really is no outside, so I'm going to say this is the outside, like that. And I've used 2, 4, 6, 8. I guess I have 2 more. And we've used 10. And we can't stop there because the nitrogen on the right only has 4 electrons. And so we've got to fix that. And let's see if I can get my eraser out. Yeah, it's working. I'm going to take those 2 away and drop them down there. You'll notice the one on the right still only has 2, 4, 6. And so I'm going to get my eraser back out and erase these 2 and then draw them down there. And then everybody seems to be satisfied. They all have a satisfied octet. So that's nitrogen. So that would go in that box. And then if we do the same thing with NH3, we put nitrogen in the middle, put our hydrogens around it, count up our valence electrons. The nitrogen would offer 5, each hydrogen would offer 1, for a total of 8. And we've already used 2, 4, 6 by just putting in the bonds. I go to the outside, but you remember for hydrogen, no dots like that. It only can have the 2 in the bond. And so once we've done the outside, then we go to the inside. And we've used 2, 4, 6, 8. We've used all 8. And you notice the nitrogen has 8. It's a satisfied octet. The hydrogens have 2. They're a satisfied octet as well. So that would go in there. Part B wants us to calculate the delta G that occurs when 12 grams of hydrogen reacts according to this reaction down here. And of course this is one of these ones where at first appearances it seems like we already know the delta G, but of course that's in kilojoules per mole. So first thing we should do is we should probably convert the 12 grams of H2 to moles. And so it's going to be 2.02 grams, and when we do the math, the answer comes out to be 5.94, and that's moles of H2. Alright, so then we want to convert that to energy, so we have 5.94 moles of H2. We need an energy conversion factor, and we're going to have the moles of H2 going to negative 34 kilojoules, because that's what it said up here in the reaction. You'll notice that it's 34 kilojoules per 3 moles of hydrogen. And so when we calculate that out, we get negative 67.32. And we should think about significant figures. The delta G had 2 in it. Our mass had 3. So I think we're going to report it to 2 significant figures. Negative 67 kilojoules. Part C is a good conceptual question that relates to bond enthalpy. It says, given that the delta H is negative 92, so it's a reaction that gives off energy, which is larger, the total bond dissociation energy of the reactants or the total bond dissociation energy of the products? You remember that if we were trying to solve this, the reactants, we have to break these bonds and energy has to be put in, and when we reform these bonds, energy comes back out. And so we calculate these values and we subtract the first one minus the second one, and we get the delta H. And in this case, the delta H is negative 34. If it's negative, it tells you that this energy that you get back when you make the bonds must be bigger, so larger, than the energy you have to put in to break them. Now this is all well and good, but let's come up with a little more formal of an explanation. So here's my explanation. The energy required to break the reactant bonds must be less than the energy released when the product bonds are reformed. This results in a delta H reaction that is negative. So connecting it back to the evidence that they gave us. That's what started all of our thinking. Now, I was a little bit worried at this point that I hadn't used their terms exactly, so you notice I tagged on this last line, the bond dissociation energy, because that's the wording they used, of the products is greater. In part D, they tell you that delta S is negative and explain why the value is negative. So I think they want you to go back up to the reaction and do that analysis of why. Well, if it's negative, it's telling us that the reaction is becoming more ordered, which of course is not favored. And we can see why we have on the reactant side we have 4 moles of gases. On the product side we have 2. And I think that that's our evidence. We just got to put it into a sentence. The delta S is negative because there are more moles of gases on the reactant side than the product side. And then I went and added the amounts because we've seen that in previous questions that sometimes they're picky about you not saying how much. And respectively means, of course, in that order. But there are lots of ways that you could say it. In E part 1, they want us to explain why as we increase the temperature, the algebraic sign of delta G changes. And so it sounds to me like the current temperature, it's negative 34, it's a spontaneous reaction, but as you increase the temperature, it becomes non-spontaneous. And we already know delta H and delta S, so the answer to this usually is in the Gibbs-Helmholtz equation. It's the same sort of rationale we've done in previous problems, and you're starting to see how frequently it comes up. So let's see if we can come up with an explanation. So this is the answer I'm coming up with here. You probably said a little bit shorter than I did, but this reaction is enthalpy driven because it is exothermic. So there's the piece of evidence that they wanted us to notice. As the temperature is increased, the magnitude of the T delta S term is increased. Since delta S is negative, the negative T delta S term is positive because, of course, if you have a negative times a negative, it's a positive. As negative T delta S increases in magnitude, delta G becomes more positive. So just sort of walking through how the Gibbs-Helmholtz equation works. E part 2 wants to know the best yields of ammonia should be achieved at low temperatures and high pressures. Explain. And you remember that actually this is the Haber process. It's one of the ones that was used to sort of identify how Le Chatelier's principle works. And if we're changing the temperature and changing the pressure, it's probably going to shift the equilibrium. So it's really an equilibrium question. But as we saw in previous questions, it's really hard to separate equilibrium from thermodynamics. So let's tackle the temperature first. Remember, to figure out how temperature will shift the reaction, we really need to write energy or heat into the reaction. Because the reaction is exothermic, it's negative 92, it's releasing heat. And you remember, as you release heat, that means that the energy must be on this side. Since the energy is on this side, as we lower the temperature, it'll shift the reaction to the right. So that's the explanation that we need to give. So this is the sentence describing what we just talked about. Because the reaction is exothermic, energy is on the product side. A decrease in the temperature will shift the reaction to the right, creating more NH3. Now let's look at the higher pressure. I'm going to erase some stuff to get some more room. Now as we increase the pressure, you remember that that's going to create a lot more pressure from where we are starting. So we've got some dots. If we increase the pressure, which of course would be like decreasing the volume, those dots are in a tighter space and the pressure is higher. Le Chatelier's principle says that the reaction will shift to the side with less moles of gas to try to relieve some of that pressure. And if we look at the reaction, there are 3 plus 1, there's 4 moles of gas on the left and 2 on the right. So So it's going to shift to the right to the side with less moles of gas. And that's all we got to do is write that explanation. Okay, so according to Le Chatelier's principle, the reaction will shift to the side with less moles of gas to relieve the high pressure. In this reaction, it will shift to the right to make more NH3. I almost forgot to say this part, that it will shift to the right, because it seemed obvious because we talked about it before. But we definitely need to say that.